Good afternoon, everyone. Welcome back. Thank you for joining us. We're glad that you're here. I'm Steve.
And I'm Scott.
And together, we're Backyard Musings Science and Technology Channel.
Yep, and we are talking about plasma.
Fusion reactor.
Yep.
Which, second only to, what's my favorite, Scott? Oh, quantum computing. Second only to quantum computing.
I'm sure somehow we're going to be able to tie this into quantum computing today.
Maybe it will provide the power for quantum computing.
Yeah.
A persistent asymmetry in fusion exhaust has challenged researchers for years. New simulations show that plasma core rotation, working together with cross-field drifts, determines where particles land inside a tokamak. Tokamaks are often described as giant magnetic doughnuts built to keep on an ultra-hot soup of charged particles suspended long enough for atomic nuclei to fuse and release energy. But even in the best magnetic cages, some of that plasma leaks out. When it does, the particles race along magnetic field lines into a specially engineered exhaust region called the divertor, which functions a bit like a high-tech tailpipe for a fusion reactor. Would you like to know more?
All right, here we go. Down in the divertor, those particles slam into metal plates, lose heat, and can rebound back as neutral atoms, which is the returning atoms help fuel the fusion reaction. In principle, designers would like this exhaust to be predictable and spread out. In reality, experiments across tokamaks have kept, we've talked about tokamaks before, I think.
Yes, we have.
And have kept showing the same troublesome skew. Far more particles ended up striking the inner diverter target than the outer one.
Where the exhaust lands determines where the heat concentrates, how quickly materials wear out, and how aggressively future reactors will need to cool and protect their diverter surfaces. For years, the most common explanation pointed to cross-field drifts inside the diverter, meaning particles sliding sideways across magnetic field lines instead of neatly following them.
The idea made sense, okay? But there was a major problem. Computer simulations that included only these drifts still could not produce the strong inner target preference seen in real machines. If the models cannot get that basic pattern right, it becomes much harder to trust them for predicting how next generation devices will behave under even harsher conditions.
A new set of simulations suggests the missing piece is not in the diverter alone, but in how the plasma moves around the entire ring of the tokamak. The research team used the SOLPS ITER, SOLPS ITER modeling code to test how particles travel under different assumptions and reported the results in physical review letters on November 24, 2025.
Their key result is that the models finally line up with experimental measurements when plasma core rotation is included alongside crossed field drifts. In other words, the spinning motion of the plasma in the main body of the tokamak can drive flows that reach all the way to the edge and reshape where the exhaust ends up.
Quote, there are two components to flow in a plasma, said Eric, MD, an associate research physicist at the U.S. Department of Energy's Princeton Plasma Physics Laboratory, PPPL, and lead author of the study. Continuing the quote, there's cross-field flow, where particles drift sideways across magnetic field lines, and parallel flow, where they travel along those lines. A lot of people said cross-field flow was what created the asymmetry, but this paper shows is that parallel flow, driven by the rotating core, matters just as much.
All right. To test the idea, the researchers simulated plasma conditions in the D3-D?
D3I. D3ID?
D3ID?
Yeah, three I's.
Yeah. Tokamak in California. They examined 4 different cases, switching cross-field drifts and plasma rotation on and off to isolate their effects. The models did not come close to matching experimental data until one crucial detail was added: the measured core rotation speed of 88.4 kilometers per second.
Pretty fast.
Yeah.
When both rotation and cross-field drifts were included, the predicted particle distribution aligned with observations. Together, these effects produced a much stronger influence than either one alone. The findings indicate that future fusion reactor designs must account for how the spinning plasma core shapes particle motion at the edge. Incorporating this connection into predictive models could help engineers build divertors that are better prepared for real operating conditions. I think it's important to do the test, see what happens, and then because they rely on these computer simulations from almost everything,
Right.
garbage in, garbage out. So taking those measurements, tweaking, measuring, tweaking, that's the thing to do.
I agree. All right.
Scott has spoken.
Thanks for listening. We'll see you tomorrow.
See ya.
Take care.